Okay, I'm continuing to look through intervals of increasing and decreasing and using the first derivative test. We're just jumping into it here. We know if we're looking for intervals of increasing and decreasing, we're going to need to take our first derivative. And then we look for critical values. Remember, critical values are when our function, not our function, but our first derivative equals 0, or when that first derivative doesn't exist. Since this is the polynomial, it always exists. So I can still set it equal to 0 to find when it does equal 0. I'm going to factor out a 4x to get me x squared minus 2. Using my zero product property, I see I have x equals 0. And right here I have x squared equals 2. When I take the square root of both sides, I get x equals positive negative square root of 2. Those are my critical values. Those are the places where my first derivative literally equals 0. So I'm expecting horizontal tangent lines, although and because they are horizontal tangents, that's probably where it's going to change direction from increasing to decreasing or vice versa. But it does not have to change direction. That's why we're being real careful when we put these values on our number line. We're going to think about what's going on around them. You know, I'm going to make this number line even larger so I have plenty of space to write. All right, so this first interval would be from negative infinity to the negative square root of 2. Then we have the negative square root of 2 to 0. Then we have 0 to the positive square root of 2. And then we have positive square root of 2 to infinity. We have a lot of places to look. Starting way down here, we're thinking, is our original function going to be increasing or decreasing right here? And we determine that by looking at the derivative and seeing, is the derivative positive or negative? Checking a really negative value in my derivative. Something really negative would get me a negative times 4, which is negative. Right here in the middle, something really negative squared is positive minus 2, so this would be positive times a negative. So my first derivative right here would be negative on this interval. And because it is negative on that interval, I know my original function y. I'm going to do this so we don't get them all confused. My original function y is decreasing on this interval from negative infinity to the negative square root of 2. Moving on, right here in between negative root 2 and 0 is something like negative 1. Negative 1 is on this interval, so plug in negative 1, and we actually get a negative on the outside. And if you put a negative 1 inside here, you're also going to get a negative. So we have a negative times a negative, which means our first derivative is positive on this interval. And because our first derivative is positive on this interval, my original function, because the first derivative is telling us stuff about the original function, the first derivative tells us our slopes are positive, so the original function is increasing on the interval from the negative square root of 2 to 0. Next section, from 0 to the square root of 2, I can plug in like positive 1. Take a positive 1, plug it into the derivative, and we do get negative values. So our derivative is negative in here. Y is decreasing. On this interval from 0 to the square root of 2. And finally, checking really, really positive values. We get out positive values in our derivative as well. Okay, and just because it's going from decreasing to increasing, from decreasing to increasing, doesn't mean that's always going to happen. You do have to check it because functions are going to play around with you. All right? you start to notice some pattern, and then you realize, oh man, I took it for granted. And just because really positive values does not mean your derivative is going to give you positive values. That does not. It could very well give you negative values. So our first derivative was positive with really positive values. So that means y is going to be increasing on this interval from 2 to infinity, or root 2 to infinity. So we have our intervals of increasing and decreasing. We know our function is always continuous. So at these x values, those points actually exist. They aren't discontinuities of any. They aren't infinite or jump or removable discontinuities. They actually exist. Those are actual points where our function did change from decreasing to increasing, from increasing to decreasing, and from decreasing to increasing again. And because we change directions at these points that actually exist, and these are points, or these are x values obtained through our critical numbers, our first derivative test is telling us we have some relative extrema. Right here, at x equals negative square root of 2, because it changes, because y changes from decreasing to increasing, we have a relative minimum. Take that negative square root of 2 and we're going to plug it back into the original function to get the actual point right there. Negative square root of 2, plug it back in. Negative root 2 to the 4th power is 4. Minus 4 times negative square root of 2 squared would be 2. Plus 5, 4 minus 8 plus 5, it's negative 4 plus 5. Yeah, negative 4 plus 5 gives me 1. So again, to get that actual point, where it changed directions, we had the x value. To get the y value, you plug it back in the original function. Okay. Right here at 0. Well, at 0, we can see it changed direction from increasing to decreasing. So, again, at x equals 0, what's going on? Y changes from increasing to decreasing. So there's a relative maximum at that point. 0, comma, plug it back into the original function, 5. Again, that point comes from the original function itself. And finally, what's going on at x equals the square root of 2? Well, at x equals the square root of 2, we can see it changes. Y changes from decreasing to increasing. And so that means we have a relative maximum. Nope. Sorry, I got caught up in looking at that last one. Decreasing to increasing is going down, and then it changes going up. That would be a relative minimum down there at that square root of 2. And if we plug in the square root of 2, it would do the same thing as the negative square root of 2. So I'm getting the same value out, which is positive 1. And it's doing the same thing because it's being raised to even powers, and negative things raised to even powers still gives us a positive answer. So a little shortcut there. But there we go. Whew. All right, a lot of stuff going on in that one. All right, you taking a look at it? You see it? You see it? You see it? All right, let's look at this on the calculator. Let's do it. Let's take a look at the calculator. I should have cleared it out. All right, we've got x to the 4th. X to the 4th. minus 4x squared plus 5 all right. There it's gone. It's gone. Okay. So notice it went from decreasing to increasing from increasing. So right here, here's a point we can see is that 0.05 is definitely a relative maximum, and we definitely said that. We saw that it was going from increasing to decreasing, and then on either side we had that square root of 2, 1, or negative square root of 2, 1, and the positive square root of 2, 1. So in order to confirm that these 2 points right there are the same 2 points that we had found algebraically, let's find those. Those are relative extrema, and we can calculate those. Go to second trace, and we can calculate the minimum. Those are minimums, remember? Or at least, that's what we noticed. They were changing from decreasing to increasing. So 3 is minimum, and I'm going to go left bound. I just kind of want to click the graph, but I have to click the calculator. Moving the cursor to the left, hitting enter. Moving the cursor to the right of that minimum, hitting enter, and then of course I'm going to guess. I'm going to hit enter again. Notice it's a negative 1.414. The y value is 1. Well, what is the square root of 2? It is 1.414. Okay, so we found it, guys. We did it. We found it. We found those relative minimums. We found that relative maximum. We can see it did go from decreasing to increasing, from decreasing to increasing. So there it is. Boom. Let's take a look at one more polynomial. This one is a degree 5. Yes, we just keep them coming. Degree 5. So we're going to take our first derivative. We're going to solve it because, again, it always exists. There are no critical values for when this thing doesn't exist. It always exists, but we can find critical values for when it equals 0. I'm going to factor out an x squared to get negative 5x squared plus 9. So I do have the x squared. X squared equals 0. Zero property says I can also set this negative 5x squared plus 9 equal to 0. Move over the 9, divide by negative 5. We have x squared equals 9 over 5. Ooh, looking pretty, doesn't it? Looks pretty. I know it's not. When you take the square root of both sides and you simplify this, it would be plus or minus 3 over root 5, which is positive or negative 3 root 5 over 5. That's pretty nice, huh? I know it's not the nicest value, but you know what? If we can do these nasty values, we can certainly do the easy values. So, number line. We have 3. I didn't finish solving this one. It was really simple. All right, we have 3 critical values, 0 and then positive and negative, 3 root 5 over 5. Throwing them down here, we have a negative 3 root 5 over 5. We have a 0. And we have a positive 3 root 5 over 5. Again, looking at the second derivative, what is it telling me? Is my second derivative positive or negative on these intervals? Did I just say second derivative? Is our first derivative positive or negative on these intervals? All right. Okay, now it took me forever to write down those intervals. We can actually think about what the first derivative is doing. Really, really, really negative values. Thinking about the most negative values you can imagine. All right? If you take these really, really negative values and you raise them to the fourth power and you square them, they're going to become positive again. Okay? But they are really big. So you can think about like negative 100. Well, negative 100 to the fourth power is something way larger than negative 100 squared. So when you multiply it then by negative 5, we've got this really large negative number, and then we're adding a smaller positive value. So ultimately, these are going to be negative. So I was looking at my first derivative, and I determined that, you know what? These values are making my first derivative negative on this interval. And we know that if our first derivative is negative, our original function must be decreasing on this interval from negative infinity to negative 3 root 5 over 3. Looking right here from negative root 5, oh man, no, negative 3 root 5 over 5. I'm sorry. That's a 5. It's a 5. It's a 5. All right, right here, negative 3 root 5 over 5. Because I'm so close to 0, I'm just going to get a quick decimal approximation of this to speed up our work here. It is, that value is like a 1.3 or a 1.34. So it's a negative. So if I look at negative 1, it is in between these values. Negative 1, if I plug it in right here, I do get a positive value. Notice, think about it. We do get a positive value in our derivative right here. So that means our original function is increasing on our interval from negative 3 root 5 over 5 to 0. On our next interval, we could look at a positive 1. If we plug a positive 1 in, we get the same thing that we got with the negative 1. So right here, our first derivative is also positive. Our function is also increasing on this interval from 0 to 3 root 5 over 5. Now let it be known, right here at 0, it was not increasing. At 0, it had a 0 slope. It was not increasing at 0, but it is increasing on either side of 0. Finally, take that 3 root 5 over 5 to infinity. Plug it in some really, really positive value. Well, it's going to be the same idea as when it was decreasing way over here, because no matter what we're plugging into this derivative, it's being raised to an even power, and so we get a positive value out from those x to the fourth and those x squared. But because the much larger exponent is being multiplied by a negative, we're getting a negative result overall. So our derivative is negative on this interval. Our original function must be decreasing on this interval from 3 root 5 over 5 to infinity. Finishing it all up. Right here, it changed from decreasing to increasing. If it changes from decreasing to increasing, because it went from decreasing to increasing, so that means that we will have a relative minimum right here. And what is that point? The x value is negative 3 root 5 over 5. And we need to plug it back into the original function to see what we get out. This one will be extra enjoyable to plug in. So let's be careful right here. I think I'm going to... all right, well, let's just plug it in. Let's just do it. We've got negative 3 to the 5th root 5 to the 5th over 5 to the 5th. You know what? You don't want to see that. All right, we could plug it in. That's a really nasty number. Our output would be whatever y of -3 root 5 over 5 would give us. All right, so if you plug that back in, we get that output. All right, at this point, if you're still watching this video and you really want to see me work that out, then you've got problems. All right, you've got problems, and they aren't these calculus problems right here. Sadistic problems. All right. Right here at 0, be careful. It did not change direction at 0. All right? It did not change direction at 0. It went from increasing to increasing. There is no relative extrema right here. There is none. It has to change direction. It did change direction again right here from increasing to decreasing. So y went from increasing to decreasing. So that means we have a relative maximum. And that x value, again, would be just as crazy as that one over there. That is the x value. And so our y value we would get by taking that 3 root 5 over 5, plugging it back in, and we get our output. Okay? I hope you're itching. What in the world does that look like? Right? You might not be that excited. I'm just really impressed if you're still paying attention to the video at this point. That was a long problem. All right, well, let's take a look at it. Let's see it on the calculator. All right, and like I said, this is the kind of problem that no one's going to expect you by hand to plug that back in and get that relative minimum or maximum. We could use a calculator for that, but we're not. Anyways, we need to know how to get it out just in case. Let's look at it in the calculator. All right, clearing out that previous one, we've got negative x to the 5th. X to the 5th plus, was it plus or was it minus? Oh no. What was it? Plus 3x cubed plus 3x cubed. No. There we go, 3x cubed. And then, what was that? Was it plus 3? After all that, plus 3. All right, graph this guy. Boom! There it is. There it is. Notice, at 0, where's my... Right there. Right there at 0, it was increasing. It kind of stopped. It stopped increasing at that moment, and then it started increasing again. Did not have a relative minimum or maximum. We did have a relative minimum right here, and there's that value. Remember, we said it was a little bit more than 1. It was like 1.34. There's our negative 1.34. It looks like our output was it maybe 0 after all that? There's no way. There's a way, I guess. And then we have the positive 1.34, the 3 root 5 over 5 right there. I'm really curious. And that's pretty much the video right there. But if you want to stick around, I am curious as to what that output was at that negative 3 root 5 over 5. Whew. Bonus content. Whew. All right, left bound, enter. Right bound, enter. Guess. Come on, enter. Ooh, the y value is like a 0.102. Yeah, I mean, we could have gotten the exact value though. And you know what? If you donate money now, I'll plug that in, and we'll figure out what that is as an exact value. But yeah, that's it.